When we talk about classical probability, we have some axiom, basic rule. So first of all, we consider omega is not empty. We do not allow division by zero. This is the definition of classical probability, that is the set E, take the size, divided by the set omega, that means the sample space, take the size. And we don't allow this to be zero, therefore this cannot be empty. The second thing is all the probability has a value larger than zero. And axiom 2, the probability of omega is 1. And lastly, this one is slightly complicated. You can think of it as a special case of inclusion-exclusion principle. So if I have a bunch of events that are disjoint, so recall what's disjoint. If A, B set are disjoint, that means their intersection is empty. That means they share nothing common, okay? Then here is the condition. The probability of a union of all these events is just the sum of the probability of this event. So basically, this is the axiom 3. We want to make sure that for disjoint events, or in probability, we call it mutually exclusive. That means they cannot occur at the same time. Then if we consider the union of both events, the probability is just sum, okay? And using 0 to 3, you can get probability of any event is bounded above by 1, probability of empty set is 0, and also this funny thing, if E is a subset of F, then the probability of E is smaller than probability of F. How do you prove it? You can read it. And then now we can talk about complementary events. So basically it's the thing from complementary set. So suppose I have an event E in omega. Now I define the complementary event of E as EC. Then EC is defined as basically the set omega subtracting the set E, okay? Then a very simple theorem is that the probability of E complement is just 1 minus E, okay? So how do we know? So here's a proof. By axiom 1, probability of sample space is 1, so we have this equal sign. And then what is omega? Omega by set definition is E or E complement. Then by axiom 3, these two sets are disjoint, so their probability or is just sum. So now I get 1 equal to the two probability added together. So if I move this E to the other side, it gives me the theorem. For example, I have tossing a coin twice. This is the sample space or the possible outcome, okay? This is the omega. And suppose I define E as at least one H. So what is the E? I can write down as HH, HT, TH. So what's the chance? What's the probability of this E? Well, by definition, it is the size of this set divided by size of sample space. So 3 elements divided by 4 elements, so it's 3 over 4. And now suppose I consider the complement. E is at least 1 H. That means EC is no H. That means it's TT. So the probability of this complement is just 1 divided by 4, so 1 over 4. So if I want to calculate, PE is 1 over 4 is exactly equal to 1 minus 3 over 4, okay? Suppose I do 3d6, roll 6-sided die 3 times. If I want to list out all the probability, I will have 6 matrix. So for the first matrix, all the third outcome is 1. And then the second matrix, all the third outcome, that means the die is 3, the outcome is 2. And then for the third matrix, the last digit is 3, and so on. I will have 6 matrix. So suppose I want this. I want to let E9 equal to the outcome for the 3d6. That means I roll 3 6-sided dice. I have a result I, J, and K. I want I plus J plus K smaller than 18. What is this probability? Well, I can use complement. E9 is just 1 minus the complement. Okay? So that means I need to find 1 minus this thing. What is this thing? I plus J plus K equal 18. That will be the set of how many IJK I have if their sum is 18. There's only one. That is the 666 case. So it will be 1 divided by the size of the sample space, 6 to the power of 3. So the result will be 1 minus this number. So that is 0.99 something. Mutually exclusive event, which basically is the set theory disjoint, which in probability means they cannot occur at the same time. Complementary and mutually exclusive are not the same. Complementary implies mutually exclusive, but mutually exclusive doesn't imply complementary. For example, I have a sample space, omega is 1, 2, 3. Event E is just 1. Event F is 2, 3. Event G is 3. So E, F are mutually exclusive. Mutually exclusive means they are disjoint. So E and F, if you take the intersection, is nothing. So empty. E, G are also mutually exclusive. So if you take E and G, take their intersection, 1 and 3 have nothing in common. So empty set. F, G are not mutually exclusive. F and G, if you take intersection, the common element is 3, okay, which is G. So F intersection G give you G, which is not empty. And then F actually is what? It's EC. So F and EC are complement of each other with respect to omega, okay? But G is not EC. G and E are not complement of each other, okay? So you see that EF are mutually exclusive, EF are also complement. But EG is mutually exclusive but not complement, okay? So here's the thing, okay? And if two events are not mutually exclusive, when you compute their probability, basically you just use the inclusion-exclusion principle. So what is it? Inclusion-exclusion principle, but in the probability version. You can prove it by using the axiom 0, 1, 2, 3, and so on. You can read it. Okay, so multiple mutually exclusive events. So for example, if I have 3 events, A, B, C, that are mutually exclusive, that means if A occur, B, C do not occur. If B occur, A, C do not occur. If C occur, A, B do not occur. If I have a bunch of events, E1, E2, E3 up to whatever, if EJ occurs, that means E or non-J do not occur. So here's an example. So I make a mistake. Okay, this should be no 2. Okay, E1, E2, E3 are mutually exclusive to each other. Here, now the 2 and the 7 are included in E2. Then when I take intersection of E2, E3, they are not empty. Okay, so they are not disjoint. So that means not mutually exclusive. So here are just some figure. So is ABC mutually exclusive? Yes. Is ABC mutually exclusive? No, because they have non-empty intersection. Is AB mutually exclusive? No, because A intersection B has something here. Is AC mutually exclusive? Yes. AC do not have intersection. But ABC as a whole, no, because AB is not probability version of inclusion-exclusion principle. Okay, so here's the 2 rule. So if AB are mutually exclusive, that means AB are disjoint in a set sense. Then A or B, the probability will be just probability A plus probability B. And if AB are not mutually exclusive, that means their intersection have something, then we have the inclusion-exclusion principle. So now suppose omega 1, 2, 3, 4, 5, 6, E1 is 1, E2 is 2, 3, E3 is 3, 4, E4 is 4, 5, 6, E5 is 6. What is the probability of this thing? If you compute all their union, it gives you 1, 2, 3, 4, 5, 6. So that means the union of all this thing give you omega. And by axiom 1, probability of sample space is 1. So you directly get 1. Here, this is just illustration if you want to use these 2 rules. So suppose I have this, then what I'm going to do is I add a bracket. Now, E1 is disjoint with all the other guy. So I can use this equation star, which basically means AB are disjoint, then I can just add them, then I get this. Now what's next? For this guy, I'm going to use this sharp. I'm going to put a bracket here. Now, E2 and this E3, 4, 5 union are not disjoint. They have some intersection. For example, 2 and 3, intersection is 3. Okay? So I'm going to make use of this equation here, doing this. So this guy becomes this guy becomes this guy, and a subtraction of this guy intersection with this bracket. Okay? And then this process gives me 3, okay? And this come here, this come here. So I have this thing. What's next to deal with this guy, right? So what I'm going to do is, well, I'm going to take bracket like this. Then it will give me this 3 thing. What is this? Again, inclusion-exclusion principle. Then I will get this 3 thing. And then I compute it, okay? Then this term will give me P6. Then now here, what's this? E3 or E4. E3 and E4 are not disjoint. They have common element. So I need to use this again. One will now become what? This one. And this thing becomes this one, which is their common element, that is 4, okay? And now we have this thing, okay? At this line, what is the probability of E1? Probability of E1 is the size of E1 divided by the size of omega. Size of omega is 6. Size of E1 is 1, so 1 over 6. What's the probability of E2? Probability of E2 is the size of E2 divided by size of omega. Size of E2 is 2. Size of omega is 6, so we get 2 over 6. What's the probability of E3? Size of E3 divided by size of omega. E3 have 2 things. Size of omega is 6, so 2 over 6. What's the probability of E4? E4 is size of E4, that is 3, divided by 6, so 3 over 6. Now, probability of this thing, well, this guy has 1 element, so 1 over 6, and there's a minus sign, that's why we have a minus sign, okay? This guy, E5 have single element, so 1 over 6. This guy, single element, 1 over 6, minus, minus. This guy, single element, 1 over 6, minus, minus. So you compute all of them, it will give you just 1.